Section 4.2 is going to expand on our ideas of complements, addition rules, and introduce the concept of two-way tables, among other things. So just some general rules of probability that hopefully will be helpful as we proceed through this lesson and the ones beyond. Specifically, for any event E, the probability of that event occurring must be strictly bounded by 0 and 1. 0 and 1 are decimal forms. If we think about them as percentages instead, what this is basically saying is that any event must occur with probability between 0%, meaning it never occurs, and 100%, meaning it always occurs. It's impossible for something to occur less than never. It's impossible for something to occur more than always. So if you're ever using one of these formulas that we're going to be using in order to calculate a probability, and you get a number that's larger than 1 or a number that's negative, you know something went wrong. It's not possible for a probability to be negative. It's not possible for a probability to be greater than 1. The absolute most a probability could be is 1, saying that it always happens 100% of the time. For any sample space, the probability of the entire sample space is 1. What that's saying is if I've properly defined my sample space and I have everything that could happen, then when I add together all the probabilities of everything in the sample space, I should have 100%. So the sum of all the probabilities in the sample space equals 1 is just another way of saying the sample space is properly listed, where I do have all the outcomes that could occur. For the empty set, the probability of the empty set is 0. So all that's saying is the probability of nothing happening is 0. So for instance, if I'm rolling a die, I can get a 1, 2, 3, 4, 5, or 6. The probability that I don't get a 1, 2, 3, 4, 5, or 6 is 0. The idea of a complement we introduced a little bit last lecture, but here we're going to go into it a little deeper. Essentially, a complement denoted E complement for event E. So this is saying E with a little exponent that's a C to mean complement is the set of all outcomes in the sample space which are not included in the event E. It must be true that if I add together the probability of an event and I add together the probability of its complement, we get 1, because the complement of the event represent everything that's occurring in the sample space. We had in the previous slide something that said the probability of everything in the sample space is 1 because that includes everything that could happen. Same way here, an event and its complement, which essentially is the whole sample space, also must equal 1. If I rearrange this slightly by subtracting the probability of event from this side and this side, that's how I get to this formula, which is useful. It says if I want to calculate the probability of an event's complement, I just do 1 minus the probability of that event. In other words, if I start with 100% of the outcomes and subtract the percent attached to event E, I'll be left with the percent attached to not E. So let's see how that works in context. A matter professor estimates that 95% of students bring a cell phone with them to class. What percent of students do not bring a cell phone with them to class? So if 95% of them are bringing a cell phone out of 100% of students, 100 minus 95 would give me 5% that are not bringing a cell phone with them to class. A classroom has 10 freshmen, 4 sophomores, 2 juniors, and 5 seniors. What's the probability that a randomly selected student in the classroom is not a sophomore? So first thing we'd want to do here is add up all the possibilities that could happen. 10 freshmen plus 4 sophomores is 14, plus 2 juniors is 16, plus 5 seniors is 21. So here we have 21 total students. The probability that they're not a sophomore, well, the one way I could get there is I could add together 10 freshmen plus 2 juniors plus 5 seniors, which would tell me 17 of the 21 are not sophomores. But the way that I get there with the complement rule is I'd take this 4 out of 21, I'd say 1 minus that. If I'm doing 1 and I'm trying to find a common denominator with 4 out of 21, I'd make it into 21 out of 21. 21 minus 4 would also give me 17. Really, it would get me there quicker if I was doing this complement rule. It would be even better if I had a list of like every possible major, and if I had 29 numbers to add up for all the other majors besides business majors, Or if I could just do 1 minus business majors, I would do 1 calculation instead of 29. So there's a lot of times where using the complement will save you some time. Find the probability of rolling 2 fair 6-sided dice and not having them add to a total of 9. The reason I include this question at the bottom here is just to show you how confusing some of the things that you might see in the textbook or in other materials would be if you're trying to look into some of these probability questions. A lot of times they assume knowledge about dice or cards or other things that I don't necessarily think students know right off the top of their head. It's possible that you love board games, you know everything there is to know about dice. If you don't, basically if I roll 2 6-sided dice, there's 6 possibilities for the first die, 6 possibilities for the second. 6 times 6 is 36 different things in the sample space. Of those 36 different ways that I can roll 2 dice, the ways that would add to a 9 would be 3 and 6, 4 and 5, 5 and 4, 6 and 3. So there's 4 ways out of the 36 possibilities, which means that probability is 4 out of 36 or 1/9. I really try not to include questions that require this much background knowledge, but if you're poking around the ebook on your own, you're definitely going to see stuff like this, so I just want to prepare you for knowing that a lot of the questions that are throughout probability in any textbook assume a certain knowledge about dice and cards that I don't necessarily assume when we talk about what you'll be evaluated for in this class. So here it's showing that if we're trying to do the percent of students, it's 1 minus 0.95 or 0.05 or 5% that don't bring the cell phone. 1 minus 4 out of 21 becomes 21 out of 21 minus 4 out of 21, or 17 out of 21 students that were not sophomores. Finally, 4 out of 36 becomes 1/9 for the possibility that you roll one of these 4 ways of getting a 9. The addition rule for probability is confusing when you first learn it, but it's intuitive if you really think about it. So basically, if I want to find the probability of E or F, most students would say if I want to find the probability of one group or the other, I just add them together and that'll give me the total. That is the start of the formula. The confusing part is this part, minus P of E and F. The reason that's in the formula is because people have been double counted by these first 2 methods. If we say E is the event wearing glasses, F is the event being female, and I have a class of 25 students in front of me. If I say everyone who's female, raise your hand. All the females raise their hand, I count and I say, well, it looks like we have 12 females in the class of 25. Then I say, everybody wearing glasses, raise your hand. People wearing glasses raise their hands, I count, and it looks like I have 10 people wearing glasses in the classroom. If I add those 2 together, 12 plus 10, I get 22 total, as far as people that raise their hand for females, and then people that raise their hand for wearing glasses. The problem is, of those 22 that I'm counting, any female wearing glasses would have raised their hand for both groups. They would have raised their hand and been one of the 12 that I had when I counted the females in the room. They would have raised their hand and been one of the 10 that I counted when I looked for people wearing glasses in the room. For that reason, anybody who fits both groups has been counted twice. They were counted here in P of E, and they were counted here in P of F. Because they've been counted twice, we need to subtract out the number of people counted twice to make sure they only count for one or the other. So if I know that there's now 5 females wearing glasses in my classroom, I take that 12 plus 10, which gave me 22, I subtract 5, the number that count for both, and that's how I get 22 minus 5 is 17. So 17 of the 25 students in my class are either female or wearing glasses. Again, the way I do it, add the group that's wearing glasses to the group that's female, and subtract the overlap. Here it's shown out when we do it without rolling a die. The probability that we get an even number is 3 of the 6 outcomes, or 0.5. The probability we roll less than 4 is 3 of the 6 outcomes, or 0.5. If we said, what's the probability you get an even number or a number less than 4? If we just added these 0.5 plus 0.5 would give me 1 and say it's a 100% chance. The problem is rolling the number 5 on a die is a real possibility that doesn't fit either of these things. Rolling a 5 isn't an even number and it isn't less than 4. So if all we did was add these two together and get 100%, we'd be wrong. Whereas, if we do it as probability of doing both, roll an even number and get a number less than 4, all that counts in that is rolling a 2, or 1 out of the 6 outcomes for 0.17. If we subtract that out, we get to the right answer, 0.83, because we add 0.5 plus 0.5, but subtract rolling a 2, which was counted in both sets. It was counted as an even number, and it was counted as a number less than 4. If we go with the idea of rolling a 5 being the only thing that doesn't count, we can use the complement rule to show we get the same probability by doing 1 minus the probability of rolling a 5. That gets us to the 0.83 that we got by using this formula above. So this math is really just showing you that yes, this formula does work. Hopefully my example about females and people wearing glasses also sticks with you, and that the idea is the formula subtracts out people who are double counted. When you get a two-way table, I'm used to books that have the whole numbers of what occurred in each of the columns or rows. For most of what you guys are going to do, I think they put it into decimal form when you're doing it in Cengage. So I'm showing you it this way because I think that's more useful in the real world. The decimal version is definitely useful, and we are going to look into that, but just know that this might be a little differently formatted than how the questions will actually be asked. That said, all the same skills apply. So what this is doing is this is showing me from a bake sale where I was selling soft pretzels and water bottles. On day 1 of the bake sale, I sold 55 soft pretzels and 40 water bottles. On day 2 of the bake sale, I sold 38 soft pretzels and 27 water bottles. What we're trying to do is find answers to probability questions like, what's the probability a randomly selected purchase was day 1? In order to find these probabilities, we want to take what were originally given as the original table without totals and find totals for every column, every row, and the table total. So we take 55 and 38, add them to find this column total of soft pretzels as 93, the total number of soft pretzels we sold over the 2-day bake sale. We take this column total for water bottles, 40 plus 27, to find we sold 67 total water bottles. We also find row totals. On day 1, we sold 55 soft pretzels and 40 water bottles for a total of 95 items. On day 2, we sold 38 soft pretzels, 27 water bottles for a total of 65 items. Either way that we do it, whether we add together the total items sold by day or the total items sold by type, we should get to the same table total. 95 things sold day 1 plus 65 things sold day 2 gets us to 160. The same way, 93 soft pretzels plus 67 water bottles also gets us to 160 total things sold. Why that's important is because this 160 is going to be the bottom of our fraction when we're trying to find the probability of any given event. So here, when we're asked to find the probability that something was purchased on day 1, what we're going to do is take the total of the row day 1, 95, put it over the total in the table, 160. If I do 95 divided by 160 and get that in a reduced fraction or decimal form, that would be the answer to this first question. Probability that something was a water bottle is everything in this column. So here I'd take the column total 67 out of the table total 160. Again, I'd put it in as division, 67 divided by 160, and I'd get a decimal answer that I would put in as the correct answer. Or I could do it by reducing the fraction to its lowest reduced form. Last question on this page, what's the probability a randomly selected purchase was on day 1 or a water bottle? This is going to require us to use the formula that we learned last time. So we know that the day 1 purchase was 95 out of 160. We know that the water bottle was 67 out of 160. So we would add those two together, 95 out of 160 plus 67 out of 160. But we need to say what's the overlap, what was counted in both groups. The thing that was counted in both groups is this cell here. These 40 water bottles that were sold on day 1 count as part of this 95 for all day 1 purchases, and they also count as part of this 67 for all water bottle purchases. So we need to subtract out 40 according to the formula. So we have 95 over 160 plus 67 over 160 minus 40 over 160 to find that probability. After we do all that out, we want it in reduced fraction form or decimal form. So here this is showing how we would get there. 95 out of 160, 67 out of 160, 95 plus 67 minus 40 would give me 122 out of 160. This two-way table shows the work status of current matter students who are in bachelor's and associate programs. So we have whether they have no outside job, works part-time, works full-time, are in bachelor's program, or going for an associate's degree. I would want to first add together the column totals, add together the row totals, and get a table total down here. Rather than go through all this, I'm just going to click ahead to the slide that has the answers here and walk you through how we're getting the answers. If we were doing it in class, I'd probably ask you guys to try it on your own. So if you want to pause the video here and see how far you can get with it, I think that's a great idea. But rather than talk it out, I'm going to go ahead and show how we get the answers. So we start by getting all these totals along the bottom, along the side. Again, I'm just adding the row. 135 and 80 is where the 215 comes from. Adding all the row totals gets me to 800. Adding the 2 column total gets me to 800. If I want has no outside job, that would be the total of this row, 215, out of the table total, 800. Is working on their bachelor's degree is this whole column total, 304, out of the table total, 800. Has no outside job and is working on their bachelor's degree. Needs to fit both things. Here's the bachelor's program, here's no outside job. What fits both things is this single cell, 135 out of the table total, 800. I can use that to figure out has no outside job or is working on their bachelor's degree by adding no outside job, 215, plus working on bachelor's degree, 304, minus the overlap that was counted in both groups, 135. When I combine these 3 numbers, that's how I get 384 out of the table total, 800. Finally, does not work full-time. To find that, we look at the works full-time row. 132 out of the 800 work full-time. So to find the ones that do not work full-time, we do 1 minus that. 1 minus 132 out of 800 is the same thing as 800 minus 132 out of 800. 800 minus 132 leaves 668 students who are not working full-time while pursuing their degrees. This is the way that it's going to look more likely when you go and try and do it in Cengage. So here, instead of giving us the raw numbers that fit into each column and row, they've told us what the probability was of each occurring in decimal form. I still use the same general math to get any of the answers they're looking for. So the first thing I want to do is add together columns and rows. 0.24 plus 0.20 gives me 0.44. 0.14 plus 0.42 gives me 0.56. 0.24 plus 0.14 gives me 0.38. And 0.20 plus 0.42 gives me 0.62. If I add together 0.44 and 0.56, it gives me 1. If I add together 0.38 and 0.62, it gives me 1. So here, you're doing a check to make sure that you've got the column and rows total correct, but always the table total is just going to be out of 1 when it's in decimal form. When I'm asked what's the probability a randomly selected family is from New York, well, the total that we're from New York is this column total of 0.62. I could do that 0.62 divided by 1, but anything divided by 1 is itself, so really, for these decimal answers, I don't need to divide by something in the end. I just need to add together the things that count, or apply the formula if I'm going to need to add and subtract. So, from New York is this column total, 0.62. From New York, N spends $50 or less, is where New York intersects $50 or less. So just this answer of 0.20. Spends more than $50 is everyone in this row. So that row total was 0.56. Is not from New York is 1 minus this column total. The total in this column was what we got here is 0.62. 1 minus 0.62 would give me 0.38. So here's those answers. From New York is 0.20 plus 0.42 is 0.62. From New York and spends $50 or less is just that one entry, 0.20. Spends more than $50 is this row total of 0.56. And not from New York is the complement of this column, 1 minus that column total of 0.62, which gets me to 0.38.